Okay, to wrap up our discussion of block cipher chaining modes, remember we said that block ciphers, if you chain them correctly, for example, using CBC mode or CTR mode, it gives you IND-CPA confidentiality. But also, remember that in our cryptography roadmap where we showed you the 4 quadrants, we said that block ciphers and their chaining modes were designed for confidentiality. They were actually not designed for integrity or authenticity. So what that means is if we have an attacker like Mallory who is able to tamper with the message while it's being sent over the channel, we're actually not guaranteed to detect that something wrong has happened. So encryption is good for making sure that attackers can't read our messages, but just because something is encrypted doesn't mean that an attacker cannot tamper with it. So to give a concrete example of what that looks like, let's say we're using CTR mode. And remember, the way you use CTR mode is you take your message, you take some pad, and this pad was generated by using the block cipher. So I encrypt with key K, and then I pass in some counter and some nonce. And then I do a one-time pad XOR between the message and the encryption, and I get the corresponding ciphertext. So let's say that the message that Alice sent to Bob is this message, pay Mal $100. She generated this random looking pad, and then she got this ciphertext. Now the problem is, when this ciphertext is sent over the network, Mallory might be able to tamper with this ciphertext and cause Bob to decrypt to something different. That's something we have to deal with. So to give you one concrete example of what Mallory could do, we could consider a threat model where Mallory knows that the original message said this. So maybe somehow there was a leak or something, and Mallory knew that the original message said pay $100, but she wants the original message to say pay $900 instead. So in general, Mallory might not know the original message, but in a case where she does, she might try to execute an attack where the original message said 100, but she's going to trick Bob into decrypting 900. That's our goal. So Mallory is going to receive the ciphertext and somehow tamper with it such that Bob decrypts something different, and in particular, he happens to decrypt the number 900 instead of 100. So that's our goal. And to achieve that, the first thing we can notice is that most of these bytes of ciphertext don't have to be modified at all. So if I don't touch any of these other bytes, I'll get the same message for the first few words. I'll still get pay, and then a space. I'll get Mal, and then a space, and the $sign, and the 00. If I don't touch any of those bits of the ciphertext as the attacker, they're all going to stay the same. When Bob decrypts them, he generates the same pad, he XORs, he gets the original message back. So if I want to change 100 to 900, the only byte that I really have to touch is this one, corresponding to the character 1. So now we can do just a little bit of algebra to figure out how should Mallory change this byte. Right now it says 58. What should Mallory change it to so that when Bob tries to decrypt it, he ends up getting 900 instead? So we could just do a little bit of algebra. It's probably more complicated. It looks more complicated than it actually is. So the first thing we can do is write out the definition of XOR. Ciphertext is equal to the plaintext XORed with the pad. We've seen that before. That's how one-time pads work. We know the ciphertext. It's 58 because that was what was sent, and Mallory intercepted it. We know the original message said 3-1. Remember, our threat model assumes that Mallory knows the original message. So she knows that the original message said 3-1. So all she has to do is solve for this unknown pad. So she can do that. This is an equation with a single unknown variable. We can XOR both sides, and we get that the pad is equal to these two numbers XORed together, which just so happens to be 69. So now we have the pad byte, and that means that actually the byte that Alice was using to encrypt the number 1, and that particular character in the sequence was the byte 69. So now that she knows the pad, Mallory can say, I want the actual message to decrypt to 900. So I'll take the character 9, which corresponds to ASCII hex 39. I'll XOR that with the pad byte, which I figured out using algebra. Now I know that instead of this byte saying 58, If I change it to 50, that's going to cause Bob to decrypt the message to the wrong value. So by leveraging a little bit of algebra and my knowledge of the original plaintext, I was able to figure out how to tamper with this byte right here to cause Bob to decrypt something different. So now, if we pass this tampered message to Bob, here I'm calling it C prime, and the prime I'm using to denote the fact that this has been tampered with. So Mallory took the original C and changed it to C prime, and in particular, we took the byte 58 and we swapped it with 50. Well, now Bob is going to generate the exact same pad. That hasn't changed. So Bob gets the same pad byte of 69. He XORs it with 50, and instead of getting 100, he now gets 900 in his message. So this is an example of Mallory successfully tampering with the message. And notice that she didn't have to know the key. It's not like at any point we gave Mallory the key. So this is an example where Mallory, an attacker who doesn't know the secret key, was still able to break integrity and cause Bob to decrypt something different. So instead of decrypting the original P, he decrypted P prime, a different message. So that's an example. Even if Mallory didn't know the original message, she could still have tampered and changed some of these bytes that would have caused Bob to decrypt something different. So while this attack assumed that Mallory knew the original message, in general, even if she doesn't know the original message or the key, she could still tamper with any of these bytes, and that would cause Bob to get a different message when he decrypts. So all of this is to say that if you use a block cipher chaining mode like CBC or CTR, you can stop an attacker from learning what the message says, but you can't stop them from changing what the message says and causing Bob to decrypt to something different. So this is why we need more schemes for integrity and authenticity, although block ciphers were a good start for confidentiality. And you can actually try similar exercises for CBC. It's a little bit trickier because it's not the case that you can just tamper with a single byte and cause the corresponding output bytes to get tampered with. I think in homework 3, you get a little bit of practice with tampering with CBC, so it's a little bit trickier. But again, you still have the same problem where whatever Bob decrypts, he has no idea of what he decrypted is correct or if someone tampered with it. There's just no way to guarantee whether Bob's decrypted plaintext is correct or it's some random gibberish. So we still don't have integrity or authenticity, although this attack is a little bit more involved. Okay, so to summarize block ciphers from today, we started with ECB mode. It was deterministic, so it was not NCPA secure. To fix that, we added in some randomness, namely the IV, and remember the IV is sent along with the ciphertext. So now when you encrypt a message, you send the message, and you send the IV as part of the message. And if you design CBC mode properly, you can show that now it does achieve IND-CPA security. Remember that just because it's random doesn't mean it's IND-CPA secure. Randomness doesn't give you security for free, but it is necessary to get security with additional being careful with your design. So randomness helps, but it doesn't guarantee security by itself. We were able to analyze some properties of CBC mode, namely whether the scheme can be parallelized, whether you have to pad the plaintext, and also how dangerous IV reuse is. Then we talked about CTR mode, and again, we showed that if you're really careful with it and you don't reuse the nonce, you do get IND-CPA security. We again analyzed the various properties of it, and we again said that if you reuse the nonce, and nonce and IV are interchangeable words, you end up losing all security. It's like reusing a one-time pad twice. And again, the nonce is something you send as part of the ciphertext. I don't think I said that explicitly last time, but it is true that you have to send the nonce as part of the ciphertext. So it's a public value. The randomness is not secret. Everyone knows it. The attacker knows it. But it's important to send the randomness from Alice to Bob so that Bob can use the same randomness to decrypt. And then finally, we showed that these schemes, while they provide confidentiality, they don't provide integrity or authenticity. So we have to go find other schemes that do provide the other properties that we want. But that's it for block ciphers and chaining modes.